Picking back up on our polar equation curves, let's graph 3C right here. Again, just graphing it on the actual calculator. We have 1 minus 2 cosine of theta. And again, the smallest cosine can ever get would be -1. -1 times a -2 would be a +2. 2 plus 1 would become a 3. So that would be the biggest radius we could ever get. By the way, if you were to allow cosine to just equal 1, 1 minus 2 times 1, well, that would be a -1, and that would still be a radius length of 1 projected in the opposite quadrant. So it looks like 3 would be sufficient. I'm going to change the window here to 3.5 to be able to have sufficient space. And as we come down here, we'll make -3.5 just so that we've got a little extra room. And you can see very fast when we graph this, you'll get a shape that looks like so. Now, you can get all types of different interesting looking shapes. We're going to see many, many of them. Things that you wouldn't have easily been able to graph by hand for sure. Our goal, of course, is to do calculus on them. So, we're going to take derivatives and so forth. But for right now, the polar rectangular formulas. Look, as we could quickly summarize, if we took a look at a point right here in rectangular, if we said, look, here's an x comma y, where we'll go x steps to the right, y steps up. Well, remember, we're going to have this distance from the pole, this distance r, and of course here is our angle that we're going to be talking about. We could have r comma theta as our polar coordinate. But look at the Pythagorean theorem. X squared plus y squared equals r squared, but we can very well keep our hypotenuse isolated. From trig, from SOHCAHTOA, you know that the sine of this angle would be opposite over hypotenuse. So sine would be y all over r. The cosine, well, the cosine would be the adjacent over the hypotenuse. So that would be down here. That would be x over r. Likewise, tangent, the tangent of that angle would be the opposite over the adjacent. So here's your opposite, there's your adjacent, you get y all over x. But guys, what is super, 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 super important, and we're going to use these two right here very, very frequently. We're going to have x is equal to r cosine theta. In other words, we could solve this equation right here for x. We could multiply both sides by r, in other words. And likewise, right here, we could solve for y. Y would equal r sine theta. You want to memorize those. Those are, without a doubt, going to be super, super, super useful. Let's take a look at example 4. It says, use polar rectangular conversion formulas to show that r equals 4 sine of theta is actually a circle. And if that looks somewhat familiar, you can see that we graphed that together in our last video. R equals 4 sine of theta. Well, here's really where we're going. When we have r equals 4 sine of theta, we're going to look up here in what I've highlighted in yellow. And we're going to say, wow, try to find some of these conversions. In other words, if I see a sine, I'd really like to see an r in front of it. If I saw a cosine, I'd really like to have an r in front of it. R alone, well, that's not as helpful. I'd like to have r squared. And we're looking here, and it's not looking very promising. You can pretty much say, well, I don't see the exact conversion that we can use up above. Tell you what, we could very quickly multiply both sides by r to get r squared. And this is doubly helpful because what I do to one side, I do to the other side. Look, I guess what I'm trying to get at is now I'd have an r sine theta. That's what I'd really like to see. On the left side, I'd have an r squared. And that's also something I'd really like to see. Because here's what's going on. This r sine of theta really could be called y. And r squared itself is really x squared plus y squared. So that's a quick method that we can use, at least in this case, to move a little bit closer to getting a very familiar graph. We still might be wrestling with, is this a circle? Tell you what, we'll subtract a 4y from both sides. And you might remember completing the square. We could very quickly take half of our linear term, half of the coefficient in front of an x to the first or a y to the first. Mr. Olson, if you had him, called this a magic box. And we're trying to find what to add in here to have a squared trinomial. So half of -4 is actually -2. When I complete the square, I put a star here because we're not done with it. But here's the square aspect. We could take -2 squared and actually get a 4. And we'll put a 4 right in here. So my right side's a 4. But now I have a squared binomial. What I put a star by is actually going to come into play. You can see this is actually y minus 2 quantity squared. And guys, this is the equation of a circle. Wonderfully, you might remember from your days in geometry, actually in algebra also, that this x minus h squared plus y minus k squared is the equation of a circle when you have it equal to r squared. Your center is at h comma k. Your radius is going to be not r squared, but just an r. So what's our center here? Well, it's x minus 0 squared. So I'd say it's 0, comma 2. Remember, this is like our k. And guess what our radius would be? Well, our radius would be 2 squared. So just like we looked at before, that's actually the equation of our circle with a radius of 2, center at 0, 2.